Okay, so let's continue on with the theorem for Pascal's theorem. So what we're going to do is first prove this theorem, and then we're going to talk about some applications. So namely the linear inequalities and also the Pascal's triangle, and we'll see how that relates to this theorem itself. Now, this theorem is actually something you could have proven after the first topic because we could actually prove using the definition of combination, the formula for combination, and we can actually prove this theorem. But what we want to do is use the concepts that we learned in set theory in order to prove this. So the theorem goes like this. N plus 1 choose R is equal to N choose R plus N choose R minus 1. Now again, we could just plug in the definition of combination and the formula associated with it, and we can show that the left-hand side is equal to the right-hand side, and mathematically we can show that proof. But I'm actually going to use a different strategy here. I'm going to use a strategy that is using the a choosing of a set, so the subsets formula that we talked about before. And it's going to go like this. So let's pretend that we have a set A, and the set A has A1, A2 has the objects A1 all the way to AN, and also it has a special object X. Okay, so X is independent of these A's. So what we're given is that the size of A, so firstly, we have these N A's, A1 all the way up to AN, and also this special object X. So I'm going to say that the size of A is N plus 1. Okay, so we have the size N plus 1 in A. All right, so I'm going to ask a few questions here, and the few questions can be answered by using the formula that we talked about before. So please recall this formula right here. The number of subsets of A of size K is N choose K, where N is the size of A. All right, so back to this. I want to know how many subsets of A has size R. And the first part, I'm going to say with no restrictions. Okay, so with no restrictions, this means don't worry about any restrictions or constraints on this problem. I just want you to answer the question. How many subsets of A has size R? Well, if the size of A is n plus 1, then surely the answer here is n plus 1, choose R, because that's what we said before. The number of subsets of size A with a particular size is the size of A, choose that size. Okay, so what about part B? So now I want to know how many subsets of A have size R and that doesn't contain X. So this special object X, I don't want it to be in this subset. So what's the answer here? Well, if we don't want the X to be part of my subset, then I think we need to do some sort of pre-processing. I'm just going to take the X and throw it away. All right, so now the size of A is not n plus 1, it's only n. So X is, in a way, not even part of this problem because I don't want X to be part of the subset. So the answer here is that I have n remaining objects, so A1 up to AN. I've thrown the X away, and I need to choose a subset of size R because I don't have any of the subsets. I need to choose all R of the items. So from the remaining n items, I want to choose a subset of size R. So it's n choose R. Okay, so now we answer two questions. How many subsets of A have size R with no restrictions? Now, how many subsets of A have size R that doesn't contain A? Doesn't contain X. Here's the third part. I want to know how many subsets of A have size R that does contain X. Okay, now we have to think a little bit here. We actually have a very similar situation as in part B, but instead of taking the X and throwing it away, we're taking the X and we're putting it into the subset. Okay, so let's pretend that I'm trying to come up with a subset of size R. So there are R elements in here. Okay, but what you're told is that X is already inside. Okay, so it does contain X. So in a way, what we've done is taken the X from the set A and put it into the subset already. So now, how many more items do we have to choose? We have to choose R minus 1 more items to be put into the subset. Okay, so let me repeat that. So at the very beginning, I'm going to take the x, the element x, from the A, and I'm going to put it into the subset. So now imagine that the x is already in the subset. And now I need to choose r minus 1 more objects. So the answer here is from n. So remember the x is already gone from the set A. From n, I need to choose r minus 1 more items, okay, to fill in the rest of this subset. All right. So I hope that makes sense, and I hope this is intuitive from what we talked about before with the size size of the subset. But I hope you can also see here that the two cases for A is B and C, right? So if I want to find out all the subsets of A of size R, then it's really all of the subsets of A of size R that doesn't contain X plus the ones that do contain X. So I hope you can see from, we'll just say from the sum rule, we have that the total, the A part, is equal to the B part plus the C part. And you see this equation is exactly equal to the theorem that we have. Okay, so it turns out that this theorem is really just talking about two cases of subsets that we are choosing. And again, I just want to stress that we could have used the combination formula that we learned in topic 1. So that is also a valid proof. But here, this would be a nice application of set theory. Now, we have this linear inequality, but what good is it? Okay, so I want to give you a very quick application. I want you to think back to when we did linear inequalities. So if you recall, there was a question back in topic 1 that said something like, how many integer solutions are there in something like x1 plus x2 plus x3 plus x4 is less than or equal to 6. Now we can assume here that the x1 up to x4 is greater than or equal to 0. So at least the bottom part of this equation is in standard form, but the top one isn't. Now what we said at the time is because this means that I'm distributing 6 candies to 4 people, that I can actually make an extra person. And the extra person is representing me. How many candies do I keep for myself? So I have essentially n is equal to 5, right? We have 5 people because I have an extra person to represent me. I have 6 candies. I could keep some for myself, right? So now we've transformed this problem from x1 plus x2 plus 3, x3 plus 4 plus x5 is equal to 6. And now we can solve it. The answer is r plus n minus 1, choose r, which is 10 choose 6. So 10 choose 6 is our final answer. Okay, so we should note that. But we also said at the time that there was a second way that we can prove it, or we can solve it using a by cases method, right? So if we're distributing 6 candies, less than 6 candies, less than or equal to 6 candies to 4 people, then there are actually 7 cases here that we can solve. We can do x1 plus x2 plus x3 plus x4 is equal to 6. That's one case. Equal to 5, that's another case, all the way down to equal to 0. So there are 7 cases altogether, and essentially the solution is summing all of these solutions together. So I'm going to sum all the equations, answers, I guess, right? All the answers to these equations together. So it turns out that if I want to find x1 plus x2 plus x3 plus x4 is equal to k, so it's as a variable k, then we have k candies, plus n minus 1, choose k. All right, so just verify my math here. We have 4 people, right? So n equals 4, and the r here is just the variable k. So essentially we have k minus, a plus 3, choose k. So what we need to do is substitute the k from 0 all the way up to 6. So really the answer is the summation from k equals 0 all the way up to 6 of k plus 3, choose k. Okay, so again, let me explain that answer. We have basically solution number one, so method number one, and method number two. Right, so method number two, and at the time we said we could use this as well, but we didn't really say much more about it. So method number two says I can do a by cases method. So all the cases for the number of candies, because it's less than or equal to six, is I can distribute all six candies, or five, or four, or three, or two, or one, or zero. And for each one of those answers, I'm going to keep it as a separate case, and I can sum them together, and I will get the final solution. So, I mean, intuitively, we can say that these two answers are the same, right? They should come out to the same answer. But do they? So this is what I want to show you right now. And I'm just going to take the summation k equals 0 up to 6. So when I plug in k equals 0, I get 3 choose 0. Okay, 3 choose 0. And then I get 4 choose 1. So if I plug in k equals 1, I get 4 choose 1. And then 5 choose 2. And then 6 choose 3. And so on, all the way up to 9 choose 6. Okay, so I'm just going to transfer this summation over to the next slide. So the summation that I end up with is 3 choose 0 plus 4 choose 1 plus 5 choose 2. And I'm just going to write everything out here. 7 choose 4, 8 choose 5, all the way up to 9 choose 6. So that is the summation we're working with. Now, I just want you to keep in mind that we had this equation that we proved earlier that was n plus 1 choose r is equal to n choose r plus n choose r minus 1. All right, so I just wanted to show you that we had this equation. So we can actually apply this equation to kind of shrink this equation. So what I'm about to do is an application of this theorem. So 3 choose 0, the in reality here is equal to 1. In fact, anything choose 0 is equal to 1. So 3 choose 0 is really the same as 4 choose 0. Okay, I can replace this without much loss of the answer here. So I'm going to take 4 choose 0 and 4 choose 1. Now, according to my equation, if I say n here is equal to 4 and my r here is equal to 1, then we can claim that 4 choose 1 plus 4 choose 0 is equal to 5 choose 1. So I can replace this with 5 choose 1. Okay, so I replace that part with 5 choose 1. All right, then I can replace this part. So again, if we use this equation over again, we can see that when n is equal to 5 and r is equal to 2, we get that 5 choose 2 plus 5 choose 1 is equal to 6 choose 2. And we can repeatedly use this application. We can repeatedly use this equation. And let's see what we get in the end. So we get 6 choose 2 here. And then we get 7 choose 3. We get 8 choose 4, 8 choose 5. So ultimately, we're going to come to 9 choose 5. So 9 choose 5 plus 9 choose 6. Right, so we're going to keep collapsing, collapsing, collapsing. So please just verify the math here. Eventually, we're going to collapse it to 9 choose 5 plus 9 choose 6, which will give me, again, according to my equation, 10 choose 6, which if we check in the previous slide, that is our original solution. Okay, so we've just verified that our solution is actually correct. So this is actually a really nice application. I mean, these types of summations actually happen a lot in counting, as you probably have noticed going through the problem sets and everything like that. So there's our first application. This is the application of linear inequalities. Okay, so this was the example we were doing was 517. Linear inequalities is just one application for this Pascal's theorem. Another application for Pascal's theorem is what's called the Pascal's triangle. The Pascal's triangle is actually a really famous triangle, and there's a lot of nice applications that stem from this triangle. But let me just show you where this theorem plays a role in developing the Pascal's triangle. Now, the first thing we should note is that this triangle is answering the question of something choose something. So n choose k. Okay. And we should note that whenever we have n choose n, and when we have n choose 0, those are always the same. They are always equal to 1. So n choose itself, so 3 choose 3, 4 choose 4, 5 choose 5, is equal to n choose 0, which is equal to 1. Okay, so the first thing we'll do in this triangle is we're going to work out all of the sides of this triangle, because these are what we call the base cases. These are called the base cases. Base cases. Okay, so up top, we have 0 choose 0, which is equal to 1. We also have 1 choose 0, which is equal to 1. We have 2 choose 0. We have 3 choose 0. And we also have 4 choose 0. So let's stop at 4. But realistically, we can keep going with this, and we can go on forever. We also have 1 choose 1 is equal to 1. 2 choose 1 is equal to 1. 3 choose 1. And 4 choose 1 is equal to 1. And again, we can go on forever on this side of the triangle. So this kind of expands its way out. Now, in the middle, we can fill in all of the ends, the nth row of this triangle, by interpolating all of the, I'm sorry, 2 choose 2, 3 choose 3, and 4 choose 4. There we go, are all equal to 1. All right, so what we can do in the middle of this triangle is, and we can interpolate through all of the different values of what we're choosing. So for example, what I mean by this is we can fill in now 2 choose 1. Now, according to the theorem, 2 choose 1 is equal to, so if I put a 2 in here and a 1 here, so 2 choose 1 is equal to 1 choose 1 plus 1 choose 0. Okay, so in the case where n plus 1 is equal to 2, right, we have 2 choose 1 is equal to 1 choose 1 plus 1 choose 0. So please just verify this in math. But where are those? Well, they're diagonally up from 2 choose 1. So essentially, we take the addition of these two diagonals and we just add them, and 2 choose 1 is equal to 2. Okay, similarly, I can figure out 3 choose 1 and also 3 choose 2. And what is 3 choose 1? Well, again, according to the theorem, it is 2 choose 1 plus 2 choose 0. So 3 choose 1 is equal to 2 choose 1 plus 2 choose 0, which is, again, just diagonal to where we are right now. So this is 1 plus 2, which is equal to 3. Similarly, what is 3 choose 2? 3 choose 2 is the addition of the two diagonals, and in this case, it is, again, 3. So it's a pretty nice application. You don't need to now, well, in theory, you don't need to come up with a bunch of multiplications in order to figure out n choose r. So let's do one more row. So what is 4 choose 1? 4 choose 1 is these two diagonals added together, we get 4. 4 choose 2 is these two diagonals added together, we get 6. And then 4 choose 3 is these two diagonals, once again, is equal to 4. So of course, this is the Pascal's triangle. It's a pretty nice application, and we can keep going like this. And I invite you to draw at least two more rows of this triangle, just to get the feel of how it works. But what is the actual usefulness of this triangle? Well, it's not really the triangle that's useful, it's the application of the triangle. So, what do I mean by this? Well, let's say I asked you a question. What is 19 choose 7? Okay. Now, in the past, we have this equation that solves 19 choose 7, and we can claim that 19 choose 7 is 19 factorial over 7 factorial over 12 factorial, and we would be able to come up with an answer. However, this is very inefficient, because what we need to find out is 3 factorials. We need to calculate 3 factorials, right? The factorial of 19, the factorial of 7, and also the factorial of 12, which is very inefficient. Doing a lot of multiplication is usually very inefficient. So, what would be a way around this? Well, we can actually turn a bunch of multiplications into additions. So, how we do that is if we wanted to calculate 19 choose 7, according to this theorem, 19 choose 7 can be broken down into 18 choose 7 plus 18 choose 6. And now we can once again solve 18 choose 7. So what is 18 choose 7? Well, it's 17 choose 7 plus 17 choose 6. What is 18 choose 6? It is 17 choose 6 plus 17 choose 5. And we can repeatedly break this down into a bunch of additions. And as soon as we hit one of these side edges, we hit one of these base cases, we can stop and we can report the answer as 1. So by far, this is a much better way of calculating n choose r than the old equation that we have. Although for any counting problem that we encounter in this course, I do prefer that you write it in factorial form. Okay, but I'm just saying that in reality, in an application in a computer, for example, we would probably do something like this instead of calculating the factorial. Okay, so this is a very nice application of this theorem that we just encountered here. All right. So far up to this point, we've introduced some set theory concepts. We've introduced some definitions. We've introduced some proofs, a few proofs, not a lot, but we introduced a lot of definitions. So right now, I want to, but mostly what we've been working on is one set. Right, so we haven't really talked about some combinations of sets or some set operations that we can work on. So the next section we want to introduce some set operations that we want to continue on with in the next video. So let me just introduce some of these set operations that we'll be using. Now, I want you to realize that these set operations are actually very similar to what we discussed in propositional logic. In fact, there's a relevance or there's a relationship between every one of these set operations. It relates to something that we've talked about before in propositional logic. So, for example, I have two sets A and B. I can make the union of the two sets A and B, and it is called the disjunction operator of each individual element. So the union of A and B are all of those elements that are in A or in B. Okay, the union is all of the elements that are in A or in B. So the union looks like this. It's kind of like a U shape, which kind of looks like an or sign, right? So that's really how we're going to remember it. It kind of looks like an or. We have the intersection of two sets, and this is denoted in this way. So this is the intersection, and it's like a conjunction operator. So all those elements that are in A and in B, so all the elements in A and in B. And then thirdly, we have the symmetric difference, which is kind of like the exclusive or, everything in A or in B, but not in both. Okay, in A or in B, but not in both. Now, how we're going to represent these is in a Venn diagram. Now, what you're seeing on the left-hand side here of this slide are Venn diagrams, which we call generalized Venn diagrams. Now, in the next video, I'll explain what I mean by generalized Venn diagrams. But for now, just know that this represents all of the different regions that an element can be sitting in. Okay, so this Venn diagram actually represents all of the regions that an element can be sitting in. When we talk about the union, A union B, we are talking about all of the elements surrounding this A and B. So we're actually talking about the elements that are taken up by this area right here. So this is all of the elements that are in A or in B, in A or in B, right? All the elements in A or in B. When we're talking about the intersection, we're talking about the elements that are in A and in B. So it's over here. And then finally, when we're talking about symmetric difference, we're talking about the elements that are in A or in B, but it's not both. So we're talking about this region here. So A or B, but not both. Okay, now we can take a very simple example. So this is the intersection and this is the symmetric difference. And by the way, the symmetric difference is a little bit different. It's a triangle. So whenever you see a triangle, it is read as the symmetric difference or the exclusive or of two sets. Now let's pretend that our set A, so let's give a quick example here. Our set A is, let's say 0, 1, 2, 3. And our set B is 1, 3, 4, 5. All right. So the union, A union B, would be, again, a set. And the elements that are inside will be 0, 1, 2, 3, 4, and 5. Okay, so 0, 1, 2, 3, 4, and 5. Okay, what are the elements that are common that are intersecting both sets? So all the elements in A and in B would be, well, we have 1 and we have 3. So we would have something like this. So the intersection of A and B would be 1 and 3. And then finally, the exclusive or, so all the elements in A or in B, but not both, is 0, 2, 4, and 5. Now, I hope you can see a relationship between these three things. So if we take the union of the two sets, A and B, and we kind of take away, right, take away the elements in the intersection, we end up with a symmetric difference, right? So if you take the first set and you take away the elements from the second set, you end up with the third set. So there is some sort of relationship that we should discuss here, and we'll do that in the next slide. But in addition to this, we have other set operations as well. So there is a complement set operation. So a complement set operation is denoted as A and then this line over the A. Right? It's denoted as A complement, is read as A complement. And the complement of A means that we have elements that are in the universe, but not in A. So essentially, it is read as all the elements that are not in A. Now we have to be very careful talking about the complement, but first let me just draw the Venn diagram. So if we're talking about a complement, we are talking about this region right here, the region that is in the universe, but not in A, right? So we have to be very careful when we're using the complement. The reason is because the complement without the universe actually doesn't make too much sense. So what I mean by this is, let's pretend that I have a set Z plus. Okay, so if I ask you, what is the complement of Z plus? Now remember what Z plus is. It's the positive integers, right? So if I say, what is the complement of Z plus? Now you might be tempted to say that, well, they're the negative numbers, including 0. They're the non-positive numbers, right? They're 0, -1, -2, -3, -4. But it's more than that. It's -1.5. It's -2.5. It's all of those numbers as well. It's also people, all Macam 101 students, right? All the countries in the world, right? Those are also in the set of the complement of Z plus because we have not identified exactly what the universe is. It's basically any object that you can think of that is not a positive integer. I hope everyone got that. Okay, so we have to be very careful to know what the universe is. If we don't specify what the universe is, then the complement of Z plus, for example, could be anything, right? Anything that doesn't belong to this set. Okay, so all right, so let's do another definition here. So let A and B be sets in a universe U. Then the relative complement of A in B. Okay, now this is a kind of a weird way of saying it, but the relative complement of A in B is denoted as B minus A. Okay, this is the subtraction of two sets. So it's defined as everything that is in B and not in A. Okay, everything in B and not in A. So if I want to define the area that is taken up by B minus A, we start with B. Everything that's in B that doesn't cross over to A. So we actually get this area right here. Okay, so we get this. And then the opposite could be, we could define the opposite as well as A minus B. And I want you to notice that the definition here is everything in A that is not in B. So everything in A that's not in B is this area right here. So everything in A that's not in B. Now notice the direction here obviously matters. So B minus A is different than A minus B. So let's do the same example as we did in the previous slide here. So if I had 0, 1, 2, 3, and if I had B as 1, 3, 4, 5, then B minus A is we start with B and we subtract off anything that crosses over to A. So we end up here with 4, 5. And similarly, A minus B, we start with A and we delete anything that crosses over to B. So we end up here with 0, 2. Okay. Now, I hope you start to see a relationship here as well, because these two things put together kind of looks like the exclusive OR. So right now, just to kind of set up for the next subsection here, I want to uh, kind of give a definition, give some definitions for A symmetric difference B. There's actually two definitions that we already seen. So this relative complement is really a subtraction of a set. So what we saw before is the symmetric difference of a set is really equal to the union minus the intersect, right? So we can say this is equal to the union minus the intersection. Right, so A union B minus B, A intersect B. Now, at the same time, we can give another definition, because if we combine B minus A and A minus B, then again, we would get the symmetric difference. So we would get something like A minus B union. Now, remember, union is or, right? So A minus B or B minus A will also give us the same definition. Okay, now see if you can verify these two, right? Just kind of intuitively verify that this is true. And what we're going to see in the next section, in the next video, is we're going to talk about some techniques to actually prove that these are equal. And just a spoiler alert, this is going to be very similar to how we prove things in propositional logic. So just like in propositional logic, how we saw ands and ors, and here we see ands and ors as well, we can prove that certain sets are equal by using the same techniques as in propositional logic. So I want you to go back, if you haven't done so, go back and review propositional logic if you want to move on to the next video. Okay, so I'm going to stop here and I will see you in the next video.